Hello Internet, my name is Quinn and this is Blondihacks. The forward push on the running gear for my A3 locomotive continues. Today we're going to finish up the drivers. That's crank pins and some retainer hardware and a bunch of little details like that. We're also going to paint the wheels and powder coat the frame and finish up a bunch of stuff that we've been building towards thus far. So let's go. When last we left our frame, it was sitting on its wheels, but of course it was all an illusion because these wheels aren't really attached and they need to come off and stay off for quite a while yet. We've got lots of running gear to do on the inside of this chassis, and of course we got to get going on the crank pins and so on. However, I thought, you know what, this is finally, I think, the time to powder coat the frame. So I'm going to do that before I go any further. I think I have established everything that's going to be touching the frame and might need to be masked off, so I can finally commit to doing the powder coating at this time. There is going to be a lot of masking on these parts, much more than I've had to do previously, so this will be some effort. What I've done is I've taped off the edges of the mating bolsters because I don't want powder coat to be under those, and so the tape is marking where the edges of the bolsters land and thus the area that needs to be taped off, if that makes sense. Well, you can see what I'm doing right now. This is what I'm doing. I use the tape to mark the edge, and then I tape off the area that is exposed when I remove those bolsters, remove the tape, yada yada, you get it. I'm reasonably new to powder coating, but one thing I have learned is that for situations like this, it is a good idea to mask the area off with Captain tape. That's a heat-tolerant tape, and keep the powder coat out of those areas. Powder coat is extremely durable. With paint, it's usually easier for areas like this to just remove the paint afterwards, but powder coat is a lot more durable, so it's easier to mask off, generally speaking. The powder coat isn't very thick, but for areas like these bearing carriers and the axle box areas, the tolerances here are extremely close. These parts fit extremely close together, so even like 1/1000th or less of powder coat in there is going to mess up the fit. So these all need to be masked off as well. I'm also masking off the interface between the cross members and the frames, because again, the fit was very close on these, so I figure it's probably a good idea not to mess that up with the powder coat in between them. I'm not being super careful with the area that I'm masking off. As long as I'm not under masking, over masking is okay. If there's a little bit of brass showing when this is done, that's fine because none of this is visible. I'm just really powder coating the inside for completeness, honestly. I don't think you'll be able to see the inside of the frame anywhere. And the nice thing about brass is that all of this coating is frankly optional because nothing's going to corrode anyway. If the frames were steel, I'd have to worry a lot about masking everything perfectly to make sure every surface got covered, otherwise rust would start to form in any area that was not covered. You can see I'm using one of the threaded holes as a ground point in my powder coating booth, and away we go. This part is too big to suspend on wires, which allows you to do all the sides in one go, so I'm going to have to do it in 2 steps for each of the long frame rails. I would have actually preferred to do the entire chassis as one assembly because none of these parts ever need to come apart again, but as you can see, it does not fit in my powder coating oven. And I went through all these drawings, looking at all the measurements, and tried to make sure I bought an oven that was big enough for the largest single assembly on this locomotive, and well, apparently I missed something. The tender water tank is what I thought was the biggest, and it just barely fits in this oven. Anyway, all that to say, hence my disassembling the chassis and powder coating all the pieces one by one, because I can just barely get the chassis frame rails in here one by one. It's very, very close. They have to go in at an angle, and there's a weird little hook thing on the side of the oven that I gotta kind of get in around. It's sort of a dogleg move I gotta do, but it is possible to get it in there without it touching anything in the oven. The nice thing about powder coating is that you can get a pretty good pipeline going. While one piece is in the oven, you can clean and prep the next one, get it grounded, get it coated, and cycle things through the oven pretty continuously. This took about a day and a half of continuously cycling parts through my oven. Each of these parts is on about a 45-minute bake because they're all quite large in mass, so there is a fair bit of time investment in each one. But here comes the frame rail now, coming out, and it is looking really good. You got to be careful at this stage. The powder coat is still fragile until it cools down. That looks really, really good. And then while that's cooling down, in goes the rear bolster. That one is on a hook because it was small enough to do this, so I could do all the sides of it at once. Get that hooked in the oven. You got to have a way to move things in and out of the oven without touching them. That's the secret to powder coating. Finish came out great on the frame rails. A little bit of orange peel, that's this Eastwood powder coat, it does that, but I actually kind of like that effect for these locomotive parts. Makes them look like steel or iron. The Captain Tape did its job like a champ. It kept the powder coat out of places I didn't want it. Can get all of that pulled off now. I did have one casualty. The rear bolster fell while it was in the oven. My hook wasn't strong enough. This is quite a heavy piece, and the hook gave out, it fell, it landed on the oven rack below and left those barbecue marks. And that surface is going to be facing upwards at the back of the cab, right where you can see it for all time. So I couldn't let that one go. This was going to have to be fixed. This was my first time repairing or redoing a powder-coated piece, so this was an interesting exercise. There's nothing magic about powder coat. It's just really finely powdered ABS plastic. And of course, a solvent for ABS plastic is acetone. So I soak this thing in acetone for a while. Periodically, I pull it out and rub off the worst of it, and then put it back in to soak it some more. I think it was actually a viewer who taught me that acetone is a solvent for powder coat, which is good information because otherwise it's very, very difficult to remove any other way. But as you can see, about 20 minutes of soaking and a little scrubbing with some Scotch-Brite, and that piece is clean and ready to coat again. After all of those parts have been run through the powder coating oven, then I can start getting things assembled once again. The masking method that I used on the ends worked really well. The bolsters all went right back on the way they came off. There was no interference caused by powder coat in those joints, which is good because they are tight fits. They needed tapping on even before powder coating. All of the fasteners have been treated with that Birchwood KC brass black. I showed this stuff earlier when I was doing the tender. It does a pretty decent job of making the brass fasteners black, and it's a whole lot easier and more effective than trying to paint or powder coat all these tiny screws. I didn't powder coat the cross members or any part of the axle box. Those are essentially all bearing surfaces, so they can't have a coating on them, and none of this stuff is visible anyway. Now, I've told my neighbors, I know I've had this locomotive on blocks for quite a while, but it's a classic and I'm going to finish it, and I'm sorry it's sitting on my lawn, but I don't have anywhere else to put it. Let's get some proper wheels for this thing to sit on. I've shown you the drivers before, of course, but we still need to do the crank pins. Those have not been done yet. And those are very, very important and very tricky pieces. I'm going to start by making a drilling jig for drilling out these crank holes. This is a suggestion in the drawings, and I think it's a good one. The thing about these crank pins is you would think the throw of the pins is very, very important. And it is, but the most important thing is that the throw on all four of them is exactly the same. There's room for adjustment in the piston and valve gear, but the four drivers will all be rigidly connected with side rods. So there is no wiggle room at all there. So they all have to have the exact same throw on those cranks. Even if the throw is off by a few thousandths, that doesn't matter as long as they're all the same. That makes this a great use case for a drilling jig. The first hole was the pre-drill size for the reamer that's needed for the crank pins, but just the pre-drill size. The second hole, I'm going to pilot drill and then pre-drill also for the reamer for the axle size, and this is going to get reamed out. You'll see how this all fits together here momentarily. But the important thing is that the spacing between these holes was set by the DRO, so that should be accurate. But again, even if it was off a little bit, that would be okay, as long as all four of them are the same. Then after reaming this out, now I'm going to make a fixturing pin that's going to go in this larger hole that's the same size as the axles on the locomotive. So over to the lathe, I've got a piece of round bar. Doesn't really matter what this is made of, happens to be 1144 because that's what I had sitting on the bench and it was the right diameter. And I'm going to turn this down to be a very close fit in the driver wheels and in that drilling jig. Essentially, I'm turning this down to the same size as the axles. Literally, as I'm sitting here editing this video, I realized I had material left over from those axles, which I could have just cut a little chunk off of and used for this pin instead of turning it the way I'm doing. You know, hindsight and all that. But officially, I'm doing it this way so that you get more sweet, sweet chip flying action. This is content. Cutty, measure, measure, and we've got a nice close fit on the driver. So far, so good. And if I did all my jobs right, then that should also be a nice close fit on the large end of the drilling jig. Survey says, result. That is lovely. All right, moving on. I'll Yahtzee this off to a length that is a little bit less than the thickness of the jig plus the drivers. I don't want them to stick down through the drivers, of course. That'll interfere with the subsequent setups. Everything then gets cleaned up and, Yahtzee, Everything then gets cleaned up, degreased, and the pin gets Loctited into the drilling fixture. Hopefully it's now self-evident how this is going to work. The pin will sit in the center of the driver and force the drill to go the correct distance away from the center line of that driver. It's actually a very close fit, and I had to get it properly aligned. It got a little stuck there. I got nervous for a moment because as soon as that Loctite encounters an anaerobic environment, it starts setting very, very fast. And I have had pieces get stuck halfway through like that in the past. Luckily, you can just break them free again with some heat and try again, but still, the struggle is real. Here's the setup I'm going to use to drill these crank pin holes. I'm going to get them centered with a close-fitting pin on the spindle of the mill. The wheel isn't bolted down yet, so I can align the two easily and zero my DRO on this point. Now, the drilling fixture is going to ensure the distance between the axle and the crank pin is correct, but I want to get the rotation correct as well. Now, that is just aesthetic, but it's important for appearance that the crank pin be well centered on the cast boss that's in the wheel. So I'm going to crank it down and use the pin to align visually with the edges of that cast boss, get it centered on the pin. It's still movable here. I've got it snug down, but not fully clamped down, so I can move it. And then I go back and make sure that my 0, 0 is still where I left it. And now I've got the boss essentially aligned with the x-axis of my mill to make sure that when the jig is in place, because I can't see the boss with the jig in place, that I'm going to be able to get that drill centered on the casting. So I move the table over on X to align the drill with the hole in the jig and then clamp down the jig. And I know that the distance is correct because the jig is ensuring that, and the hole will be aligned with the casting because I've aligned it previously with the x-axis of the mill. I hope all that made sense. I'm not going to claim this was the easiest way to do all that, but this did work for me, so can't argue with results. Well, you can, but I wish you wouldn't. I went a little extra deep as well into the wood to make sure there's clearance below the hole for the end of the reamer. Speaking of which, in comes the reamer now, but out goes the drilling jig. That guide hole is just the exact size of the pre-drill. The reamer doesn't need the guide because the reamer will follow the drilled hole. And we do need the guide for the drilled hole, so either you make 2 jigs, one for the pre-drill and one for the reamer, or you just make one for the pre-drill because the reamer doesn't need it. There's the final result for the first wheel. It certainly looks nice. The hole ended up nicely centered and the distance looks about right. We won't know for sure until I build a whole bunch of valve gear to go on these pins, but as far as I can tell, all 4 of them came out identical, and I think they look pretty nice. That was a stressful job because those are valuable castings, and I only had one chance to get that right, but we did it, and now I can take out my stress on this piece of tool steel round bar, which is going to become the crank pins. Yes, I have many power tools that would do this, but hacksawing is good for the soul once in a while. With the blanks rough cut now, it's over to the lathe to face off one end. And we're going to put a center in the ends of these, not just because we're going to need that center for manufacture, but also because, of course, on the real thing, crank pins and such always have centers in them. So it's a kind of an important aesthetic detail for locomotive crank pins. And of course, on the real thing, the centers are there because that was needed for them to make them. The real ones actually probably have centers on both ends. I haven't actually checked because they were probably turned between centers. Luckily, that's not necessary here. I can just pull the part out, give it some tail support, and do a standard turning setup, and that will be just fine. I'm going to start by turning the piece overall down to 282, which is just slightly larger than the top of the tolerance of 3 separate diameters that need to be on this crank pin. The tricky thing about these pins, they look like just pins, but the tricky thing about them is that there's 3 separate diameters that all have very, very close tolerances. You can see in the drawing how close these numbers are. We're talking about a couple of tenths on some of them. These are without a doubt the closest tolerances I've seen on this project so far, and possibly on the entire engine, I'm not sure yet. Now the thing working in our favor though is that the widths of the diameters do not have much tolerance on them. These are very generous. So we can get a little sloppy with where these lines are, just laying them out by hand is fine, but what really matters is that we get the diameters of each of these 3 sections really, really dead nuts on. So I'm going to do that with emery paper. Emery is of course not a fast way to remove material, but it's a very, very controlled way to do it, and as a nice side effect you end up with an amazing finish, and it's pretty darn hard to overshoot a dimension with emery because it is so slow. I use 320 grit emery for this, and I use it with cutting oil, which helps keep the sandpaper from clogging up, which makes it last longer. However, that does slow down the cutting action. The rule of thumb is using emery with cutting oil roughly doubles the grit. So my 320 becomes 640 grit. So it cuts slower, but because the paper doesn't clog up, you can use the same piece of paper for a long period. If you use it dry, the paper clogs up instantly and you go through a lot of it. So I'm not sure that it's actually faster to use it dry, even though the grit is lower. But from here, it's just sand and check and sand and check and sand and check until you get down to the dimension. Here's the result of that first diameter. We're at 281 3/10. So I'm right on the top of that tolerance for this section. That's right where I want to be. Very happy with that. I'm going to move on. One down, 2 more to go. Fair warning with this method, you really want to get within 1/1000th of the final dimension with the cutter before you go to the emery, because this is very slow. This was about 20 minutes of sanding for each of these 3 diameters. And then of course I have 4 of these pins to do. With the 3 diameters established, I'm ready to part this off. However, I'm not actually going to use the parting blade all the way through. I'm just going to mark the location of the cut with the parting blade, give myself a little bit of a starting notch, and I'm actually going to do this with a hacksaw. If you're a regular viewer, you know I've done my share of parting tool steel, sometimes pretty large diameters of it. It can certainly be done, but it's pretty stressful, honestly. Tool steel is very grabby on that parting blade. It's very sensitive to your surface speed being exactly right, and I've shattered my share of parting blades in tool steel. So these days I prefer to just hacksaw it off over length, flip it around, and face it down to length. So much less stressful. I wrap the piece in some soda can to protect it from the jaws. We just spent quite a bit of time achieving a beautiful polish on all of those surfaces, so I'm not going to mess them up with the chuck jaws now. And then face this side down to length. The reason I used tool steel for these crank pins is because they are going to be hardened. These crank pins are essentially the inner race of a bearing, so they are going to get a lot of wear and tear, and it's thus recommended that they be hardened and tempered. So start with the hardening. I heat that to cherry red, and then dunk that in oil, swirl it around in the quenching oil. I'm using canola oil for this because it makes the shop smell like French fries. Once that's cooled down, then I clean the soot off with the Scotch-Brite wheel, and it's now extremely hard, too hard in fact. Now it's brittle, so then we temper it. I did a whole video on heat treating in the home shop with a simple torch like this if you want to know all the details, but at this point now I feather the torch on it very, very gradually, keeping a very close eye on it. As soon as I see a little bit of yellow start to appear on that surface, then I grab it and I dunk it in water. And the water here is not a quench because we haven't heated it up to that cherry red temperature. The water here is just stopping the heat so that the temper stops exactly where I want it. And that is just what I wanted, a nice even kind of straw yellow color all the way around. Then I check the dimensions because heat treating can change the dimensions of a part. Not usually with little parts like this, but it's always good to check. If it grew a little bit, then you can sand it down a little bit on the lathe again. I'll do a little dry fit on the drivers as well. That is a very, very close fit. That's actually excellent. That is almost an interference. That's probably what's known as a locational transition fit, somewhere between like a plus or minus 1/10 clearance versus interference. So that's probably a light press. I don't want to push it in because I may not be able to get it out, but that fit is excellent. And of course I need 2 of those, so I did all of that again. The front crank pins are shorter because the side rods go past them. They're made basically the same way. There's only 2 special diameters on them. Again, similar extremely close tolerances, but only 2 of them this time, so they are a little quicker to make. The difference with these, though, is that they have a large T-pin that goes through them and retains the running gear on these pins. So for that, we got to drill and ream all the way through the centers of these pins. The rear crank pins actually don't need anything holding the rods in place because they're held in at the front. Once again, parting by hacksaw. I don't have a lot of depth on this lathe, which is why I'm only using short strokes on the saw, but it still works fine. And once again, those get face down to length and heat treated just like the long ones. On those short pins, I had to mark which end is which because they're symmetrical end to end. Otherwise, I would lose track of which end is the narrow end with that special diameter on it. Now, back to the lathe with some of that 1144 stress proof, because I'm going to make some T-pins, and these are what goes through the centers of those holes in the front crank pins. These are very long, skinny pins, and they have a groove in them for a snap ring. Because of that, I'm only working in short sections at a time, starting at the tailstock end and moving towards the chuck. That way I've always got rigidity because I've got the thicker stock behind it supporting the section that I'm currently working on. This is a way to do long, skinny parts without using tail support and thus requiring a center in the middle of your part. With a little section at the end, then turned down to final diameter, I can come in with this grooving tool, which I ground off camera on the bench grinder with a piece of high-speed steel, and that's an 18/1000 wide grooving tool. Very, very skinny, but that's to make a very tiny snap ring groove. This being the snap ring in question, this is a 1/8 snap ring, which I think is the smallest size they come in. It's very, very tiny. In fact, it's so small that the standard snap ring plier sets that you can buy are too big for these. You got to buy very special tiny snap ring pliers that you can only get at specialty tool suppliers. And so, of course, I don't have any because I have the same crappy set of hardware store snap ring pliers that everybody has, and they don't support this tiny size. So I tried various methods for getting this thing on. Nope. No, what about, yeah, if I just, nope. Maybe if I, yeah, and then just pull, yeah, oh, yeah, that's working. And yeah, it's pull a little harder, and that's broken. Okay, well, we'll get another one. I've got lots of them. They come in boxes of 1,000, and no, not going to go that way. What about if I get this in there and then kind of twist, and then kind of push the apart? No, ooh, but 2 picks maybe, and then just kind of pull and push, kind of, and then twist and pull and twist and push and twist and pull while pulling and twisting and push and twist. Nope. Well, that's gone. I gave up on that, ordered the fancy pliers, looked at the drawing again and realized it's supposed to be an E-clip anyway. And those are easy. So that all happened. With that drama behind me, I can now turn down the rest of the pin, again working in sections, working towards the chuck to keep my rigidity as I go. Quick test fit to make sure my dimensions are all correct. So the short crank pin goes on like so, and then there should be just enough room to get the E-clip in behind it. That seemed to go on nicely, and the pin can spin reasonably freely, so I think that E-clip isn't pinched or anything like that, so that all looks good. And now I can part this off to length. So you can see how it leaves a big flat head, making kind of a big specialty T-pin type of thing. It's kind of a nice looking part, actually. Again, one of those things where it's a simple part to look at in the drawing, but making it correctly is actually tricky because of the little details. All right, let's get some paint on these wheels. I'm going to use the same red paint that I used on the tender wheels so that they match. I start by degreasing, cleaning, and masking them. I learned on the tender wheels that the easiest way to mask these is to simply cover them in tape and then cut away everywhere that I want paint. With recessed castings like this, that seems to work very well. I start with a light dusting of acid etch primer, and then I hit it with, as I said, the same red that I used on the tender wheels. If you've been watching this series, you know I didn't actually love this paint. It's part of why I investigated powder coating in the first place, but I used this on the tender wheels, so I'm kind of committed to it, and it works okay. The insides of these wheels aren't subject to a lot of abuse, so even if it's not the most durable paint, it'll be fine. As with the tender wheels, now I'm going to do a polish on these using that same setup. If you watched the tender, this is a plate that goes in my chuck, and I've spray glued some 320 grit emery. The chopstick and the tailstock is there just in case the wheel slips out of my hands, doesn't go flying across the shop. This works super well, this setup. That's just about 10 seconds or so of polish time, and here it is side by side with an unpolished one. You can see what a nice difference that makes. It's not just for appearance, that's also corrosion protection. The finer the finish is on a metal surface, the longer it will take to corrode. And cast iron is actually pretty corrosion resistant as well, so it'll last a really long time. But just in case, I'm also going to hit it with some Bow-Shield T9 on those machined surfaces. I've got the tread taped off because I don't want this stuff on the tread where it might interfere with traction. Traction is already an issue on model locomotives, and cast iron makes that worse. Real steam locomotives have steel tires that are heat shrunk onto the cast iron wheels because cast iron is actually pretty inherently slippery. It's not a great material for wheels, but it's the best we can do on these models. I'll do another test assembly now. Once again, I'm not pushing any of these pins in all the way into their final positions because this all has to come apart a couple more times yet. We have more mechanical and running gear components to do inside the chassis before we can fully assemble these axles for good. but I can at least mock it up and give you a sense of what things are going to start to look like. You can see the running gear starting to take shape now, so it's getting pretty exciting. Pretty soon we're going to have side rods on there, and that's going to be amazing. Well, this is a lot of progress, I think, for this video, so that's where I'm going to leave it. Thank you very much for watching, and thank you so much to my patrons who make all of this content possible week after week, including donating castings like these wheels. As I mentioned before, these were a donation to the channel, which really gave me a leapfrog ahead on this part of the project, and I'm super grateful for that. Thank you very much for watching, and I'll see you next time.